Binary. The end. Okay, thanks for watching. Nah, I'm just kidding. Time to talk about some things. I haven't done one of these in a while, so I figured I was due. And I don't have as much time as I used to do these, at least not yet. So I thought I'd take on some common programming tasks that are always coming up, kind of like the Swiss Army knife of coding, common tasks that I encounter, and explain them the best I can. And do those in C because C is an easier to understand language. The first one that comes up might not be the most common, but it's pretty important, and that's binary and working with binary directly, or I should say bits, and how you might do things like common tasks like setting a bit, inverting a bit, flipping a bit, and checking to see if a bit is set and things like that in C. And maybe embedding some information in cases where you're extremely data constrained or bit constrained as far as every bit counts, that kind of stuff. So first and foremost, I'll just define what a bit is. So a bit is short for binary digit, and a binary digit is one digit of a binary number. And as you guys may or may not know, binary numbers are numbers that consist of only bits or binary digits, meaning that they're zeros or ones. You can only have a 1 or a 0 for each digit, which basically means every digit can be 0 or 1, and you start considering that you're working in powers of 2 or a base 2 number system. The reason why bits are convenient in C, you should not use them indiscriminately and think you're cool because you're working with 1s and 0s. I mean, printf can't even print binary by default. That just goes to show you how not useful it is to actually look at the binary representation of a number all the time. But if there are cases where you find yourself needing bits, it's really useful. The one case where I find it's useful is for flags. So that's kind of probably one of the most common cases I find myself using bits. For example, suppose I had like a struct, right, thingy, and my thingy had a bunch of attributes that might be common for a game. But suppose, for the sake of keeping alignment, right, let's just suppose for really stupid reasons this was short, so 2, 4, 6. Well, I will keep this int. Suppose for the sake of keeping alignment or for whatever other reason you might have, you're very constrained and you want to have 8, or let's just say more than 1 possible Boolean flags that you want to set for your particular thingy object. One example might be like if this was a game character and you wanted to have a flag for like whether or not he was dead, whether or not he was like invisible or temporarily blinking and vulnerable. Another flag for whether or not he had like a high jump thing set, maybe some items he acquired. You can think of a lot of things where you want to combine a lot of Booleans or Boolean true-false expressions into one number. The benefit of being able to manipulate the individual binary digits of a variable is that if you had a single byte, you know that 1 byte is 8 bits, and therefore you have 8 binary digits or 8 bits that you can actually change or manipulate in one variable. So let me kind of explain that real quick. Thingy. So by starting this thingy flags field out to 0, you basically have the number 0, which is all bits are off. So I'm pulling up this mat calculator here, which has, if you go to command 3, it has a binary mode. So obviously if I put 0, it shows that it's a 64-bit number instead of an 8-bit number, but you can see all the bits are set to 0, which is a very useful thing. My C is a little rusty, you'll have to bear with me. So that sets everything out to 0. Suppose I wanted to set just the first bit of flags and leave everything else alone. Well, the way I do that is I use the OR operator, and what a binary OR operator does is basically takes a series of binary numbers, that's what it is, a vertical bar, and ORs those things together so that essentially if one or the other one is true, the result is it's like a logic OR. So either one is true, you'll get a 1. But if none of them are true, you'll get a 0. And it does that for each digit independently. So you can basically OR all the bits together of the entire 8-bit number and get the result. Kind of ignoring some of that and just thinking about how do I set a bit, the way you do that is you OR equals. So basically you do flags, OR equals, and then the bit you want to set. And by me ORing it with 1, 1 is also binary for 1, as you can see here, the first digit 1 being set. So by ORing 0, or ORing the number with 1, the result is that 0 or 1, you've set the first bit. So this basically sets, so that's one flag's been turned on, the rest of the flags are left alone. If I do it again with 2, now the first 2 bits are set. So what I'll have here is I'll OR this with 2, and you'll see here in the binary representation here, both the first and second bits are set, and so forth. Now, a common rookie mistake is to say, well, let me do 3 for the third bit, but in reality, what you want to be doing is always increasing in powers of 2, because if you look here, 1 is the first bit, 2, 4 is the third, 8, 16, so you double every time. And each power of 2, each even power of 2, is one of the first 7 bits for an 8-bit number. If you tried to go past the end, for example, 256, that is actually the 8th bit, and that would overflow or be too high of a bit to set for this 8-bit chart character data type. So we basically, at this point, if I wanted to set just the first 4 bits, 1, 2, 4, and 8, I will have done that. Get rid of this toilet. And I ask printf to print the numeric value of my flags, and I get 15, which is consistent with all first 4 bits being set. 15 in decimal, not hex, which I might cover either in this video later or in another one. 15 is, the binary for 15 is 1111, and then no more zeros, because you basically combine the first 4 bits, and then that's what you'll get. So essentially what I've done here in programming lingo, or I should say bit logic lingo, is I've set the first 4 flags. And again, these could be whatever I want. A lot of people will pound define these. Maybe they'll call this one like high jump. This one might be like stronger ammo. Whatever you want for each flag, as long as they're a power of 2, is really important. So if you want to check to see whether one of those flags is set, all you have to do is do the bitwise AND on the flags, and the thing you want to check to see is set, and then you can basically say like so. And if you guys probably, and of course third bit is set, if you guys haven't probably already guessed, a bitwise AND works the same way a bitwise OR does, except both bits have to be set. So if you have something like this, and you AND it with something like this, you will end up having 0, 0, 1, 0, because the only case where it works is when both of them have been set. And what a bitwise AND does is basically say if the result of the flags and 4, remember 4 is, can I type today? 4 is the third bit, so basically what we're checking to see is if 15 and 4 result in anything that's not 0, which is basically this bit is present, then we're good. But layman's terms, or a way to think of this more naively, is bit 3, or is 1, 2, 4 yet? Is that third bit set? Now, suppose I wanted to disable or unset just one of the bits. Well, it's actually pretty easy. Well, it looks a little weird syntactically, but it'll make sense when I show it to you. It's the hardest one to memorize when you're starting out. What I typically do is I will just type it out, and I'll show you. AND equals not the bit that you want to set, and then that will essentially turn it off. So I run, and it's turned off. And what you're basically doing here when you do something like this is you're using the not, the logical not operator, which flips every single bit with respect to all the bits that are possible that can be set. So you can think of not 4 as all the bits except 4 being set. So if I take not, we're going to get a huge number here in the calculator because it's going to essentially flip all of 64 bits. Yeah, there you go. If you look at all the 64 bits here, The logical NOT, or also sometimes called the ones complement, basically turns all the bits except the one that you specify on, and then turns that one off. And then by AND equals with it, basically what that does is it's saying that now we only want all the bits except, so basically all the bits will succeed if they were already present, because these are all ones, except that one that I'm setting to 0, and that basically results in that bit being cleared. This is probably the hardest one to think about logically, is like what exactly is going on. But you can always be guaranteed that if you do AND equals not the bit that you're setting, it will clear that bit. And that's how you work with bit flags. So binary flags, or bit setting and clearing aside, another very common application of working or needing to work with directly with binary bits is encoding information into color buffers. This is very commonly needed for things like GPU computing, where you more or less know that you're stuck with 32 bits per pixel for each pixel of the color buffer, and you might want to encode general information into those bits so that you can do general computing using the GPU. This is commonly done in like applications for like WebGL, where you're stuck with an older OpenGL standard for shaders to work with and so forth, and you know that you're stuck with an entire, or really only 32 bits for your entire color. First, let me kind of explain the history of where that 32 bits came from and why that's a thing, and then I'll talk about how you can play around with that. So 32 bits per color. 32 bits is the same size as an int. And you will often find that the encoding for color into an int is typically something like RGBA, where each of these tuples is one 8-bit number. So for example, red, green, blue, alpha, and then those numbers are typically represented in hexadecimal, where each F is 4 bits, and you will have each 2 Fs is 1 byte, and then you will have 4 bytes. So FF, 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 FF. And this is kind of considered the white or full bits value for a color. So for example, red, green, blue, and alpha. Sometimes it's in the reverse order depending on how the GPU wants to mess with it. That's not as important as, well, you'll just be able to flip the order of what you're working with if you're concerned with this. But this is another application of hex, because hex can represent very large numbers with less digits without having to type out binaries. So this is kind of very brief. Don't consider this a full video on hex. Maybe I'll do one later. But this is essentially how you represent all 32 bits being set for a 32-bit number. If I switch this back to decimal, you'll see that a 32-bit number can represent a maximum of 4 billion possible unique values. It's 2 to the 32nd. So that's what happens when you keep going up in powers of 2 and get really large. But typically people don't think about the full number representation of 32 bits when they're thinking about color. They're really only thinking about each of these bytes at a time. So in the same way that we might want to access and play with, just telling printf to print this thing out in hex for me. Good. See it down here in the bottom. So typically in the way we might want to implement or manipulate individual bits when we're working with binary flags, it's common for us to want to manipulate individual bytes or colors of a 32-bit number when we are messing around with colors. So let me kind of explain how one might do that. The first thing that you're going to need to know when you're messing around with this kind of stuff is bit shifting. So switching out to hex here, if we had a number FF00, you see the second bit has been set, or I'm sorry, the second byte is all ones, and there's a gap here to the right of zeros. What bit shifting allows us to do is shift up to 1 bit at a time, right or left, the binary digits of a number. So the idea here is we can hit shift right, and you see the bits were now been shifted 1 to the right. We can shift left as much as we want. And this operation is represented in C with 2 less thans or 2 greater than icons respectively. So for example, if we wanted to take this C number and bit shift it to the right, we basically can do this. C double right shift equals 1, and then we can print out the hex for that. So you can see if we took C and bit shifted it by 1 bit to the right and made note of the hexadecimal value, we basically end up with a number that is the same as the original, except one bit has been shifted to the right. And off the right edge, the bit is essentially lost. So let's take our number that's completely full of ones and actually set it something a little bit interesting. So now we basically have a distinction here of all four colors, or all 4 bytes of our number represented by A, B, C, and D. Suppose I wanted to determine what the third from the right, or second from the right byte, the C, or the B value in RGBA terms. Suppose I wanted to see what that is. Well, combining the knowledge that I had before of bit shifting and binary operations for ANDing, I basically can take this number and ask myself for the B value and basically take it, shift it to the right 8 bits, and AND it with 0xFF so that anything to the left of the first byte is dropped, and I can actually ask myself what that number is. So at this point, I've extracted the second from the right byte. So that's how I extract B. I could follow the same rules to essentially get red, green, blue, and alpha out of the number are the same. So if I wanted red, I'd actually be shifting 24 to the right. If I wanted green, it'd only be 16. Blue we've already done. And A, we don't shift anything. And at this point, we should be able to print out RGB and A together. Oops. A, B, C, and D. So again, what we're doing here is we're taking the number. We are shifting it to the right so that we basically want the number, or I should say the bytes, the 8 bits, that we are interested in to be in the right position of the from 0 of the number. So the way we obtain that is we basically shift the number of bits to the right that the number is. So D, which is the alpha channel, DD, is already in position, so we don't shift it at all. C, we shifted 8 bits to get into position. B, we would do 24. And double A, we would do 24. Or I'm sorry, B, we would do 16. Double A, we would do 24. So by taking this number and shifting it to the right by 24, you see that we obtained the original double A that was originally all the way to the left, and now we have it in the right position. And if there were any numbers to the left of it, which wouldn't actually apply in the case of R, because there's already the leftmost value, but just for the sake of interest and consistency in learning, we'll leave it in there. If there were any numbers to the left of it, the AND operation, 0xFF, makes it so that only these bits are kept. So example, A, B, C, D. We go here, bit shift to the right, 16, go back to decimal. This is the case where the ANDing of FF is needed to get rid of this AA on the left so that we can extract just that byte. So for example, AND FF, and now we only have the B. So that explains this process of actually splitting the bytes of this variable out into individual components. The reason why this is useful is if we wanted to actually do operations on the individual colored channels, we could do that by actually playing with reassigning or doing whatever we want to. So for example, if I wanted to change the B value to be 0x44 instead of 0xCC, I can change it like this, and then I could essentially rebuild or recompose the C value from the original 4 bits and take into account the changed B. So the idea here is we take R, double S then 24, and shift it back into place. Logical OR that with C, double shifted left 16. Not C, sorry, green. B, 8. Again, these are left shifts now. And then A. And by us doing this now, we've rebuilt our 32-bit number with the changed B value to 0x44. You'd think after coding this many years, I wouldn't forget to put \n at the end of my printouts. So we have A, B, 4, D. So you can see that I've actually been able to extract, change the B value, and recompose the number. So that's kind of an idea of working with the individual bits of a 32-bit number. Now suppose, this is what makes this stuff interesting to me. Suppose these weren't colors, suppose these were any other kinds of information that you possibly could want to manipulate. You can now take those things and encode them into a 32-bit number all the same. So this will be the last example I go through because I know this stuff's pretty cryptic to people starting out, but hopefully you're starting to see the value of this stuff. Let's suppose for a second that these were not colors, but information that one might use in, say, like a 3D editor or something like that. And let's suppose that in every single pixel, you have embedded into it an object index, a sub-object index, and then some other kind of flag. So just for personal preference, I'm actually going to put the flag first. So we basically have a flag, which is kind of a general purpose, could be, one of two things. An object index, which we ideally would want to store as many objects as possible, and a sub-object index, and maybe let's consider that there won't be more than 256 sub-objects. So you kind of understand my thought process here, because we're limited by 32 bits, and we want to store all this information in them. Well, we know for a fact the flag is going to take 1 bit away. So let's look at our entire range. We have all 32 bits here. We're losing 1 bit already for a flag that we need to encode. So basically I'm going to shift this to the right. So that's 1 bit that's been lost. If I go into decimal here, we can see we've already went down from 2 billion possible values in our object index domain down to 2 billion. So 4 billion down to 2 billion. And we know also that we're going to need 8 of these bits for sub-objects. So in other words, flag is 1 bit, sub-object is 8. That leaves us basically with only 23 bits for the object itself. If it was 24, just from my own memory, I know that 24 is 16 million. But we've lost half of those because we decided that we need this flag, so I'm going to divide this by 2. We're left with 8 million possible objects that we can store. So this is a way of thinking like the way those colors were split up, but instead of splitting things up at even byte boundaries, now we're basically saying first bit is this, next 23 bits is that, last 8 bits is this. So I don't really know what this number would be because I don't have a concrete example of, something. But we might just be able to use this A, B, B, C, C, D, D. But now, instead of extracting these things out evenly, we can basically extract them out based off of the information we know we may or may not want to put in them. So we're going to make a static function here, and it's going to do 2 things. One is going to be our builder. And what this basically is going to, it's actually going to return our int. It's going to return all 32 bits. And what build is going to do is it's going to take the arguments. This could be a char, it doesn't matter. The flag, the object index, and the sub-object index. And it's going to return the proper binary number that can encode all that information. Again, this is neat because you're encoding different things into one variable, which can go into one color buffer or any other case where you find that you might be limited by the number of bits that you can use. And then we're going to have I guess you can say, I don't like build anymore. I think I'm going to call this pack, and I'm going to call this unpack. And what unpack is basically going to do is it's going to take the 32-bit index. This needs to be unsigned, by the way. It's going to take the binary number, and it's going to return to us by reference the sub-object, the flag, and the object, respectively. So let's look at the build case first. The build case shouldn't be too bad. It's the same bitwise ordering we were doing before, except now it's not essentially as even. So by packing the flag, we know for a fact that the flag basically needs to be shifted 31 bits to the left. So if this was our flag and we shifted it 31, we'd find it at the very top of the number. We do not want it to spill over to this. It would overflow the unsigned 32-bit integer. We want it to end up right here. I always find myself using this calculator to double check myself. Then we want to OR combine it with the object, and the object again is 23 bits. So we basically want to take the object and we want to shift that 8 bits to the right because that should leave enough room for the sub-object. So let's just look at this real quick. This doesn't matter what this number is per se, except that it needs to be shifted 8 bits to the left. And what this allows us to do is leaves this space. Now there is one tricky thing here that I'd like to do with this object before shifting it, because I do not want this object to corrupt the flag if it's greater than, what's the word? If it's greater than 24 bits. So we actually need to AND this thing in advance. This is just some safeguarding here, so that if the number would have overflown, it won't. And we basically end that with 23 bits. 23 bits, again, should be 3 Fs divided by 2, which is this number here. And again, I didn't pull this number out of my ass. You can see that there's this. What I did was I started out with 24 bits because I know how to type that out. I divided it by 2. Again, just a little Swiss Army tip. Dividing something by 2 is exactly the same thing as bit shifting it to the right, if you want to ever do that in coding. And then bit shifting to the left is the same as multiplying it by 2. So I basically shifted it 1 to the right. This ends up giving me a 24-bit number, which I can then AND with the object index to safely make sure that it is always less than those 23 bits. And then that builds that. And then last but not least, I take the sub-object, which does not need any shifting, but does need to be indeed ANDed with 8 bits to make sure that it does not overflow. And this basically should build, if I didn't screw it up, the result here. This thing shut up. Make me look stupid. Okay, so that's our pack variable. So basically I can have here sign int data pack, let's just say 1. Oh, I don't know. 1 million. 1. And then a sub-object can be anywhere between 0 and 255. And what this does here is creates a variable here. Doesn't really matter what this is. It's just it's the result of all of our stuff packed into one number. So if we actually paste this in, what we see here is we have the first bit set. Some of the bits, oh, it should not be a less than. That's why it's good to check. Jeez. I love how C lets you do stupid things without any problems. That would have been really bad. I'm going to check your math. There we go. That's better. First bit set. Some of the bits have been set here to represent our 1,000,001 number, and then this number right here should be 120 in binary for this final right byte here. It is. So now we're going to use unpack. Unpack is going to take a given binary number, and it is going to get that stuff back out of it. And what we're going to do is we're going to call the function on it and make sure everything works. So the first thing should be the simplest thing to get out should be the flag. We basically just check to see if the boom, this is fucking wrong. What I'm typing here right now is wrong, and you'll see why later. It'll be fun. Just wait. Flag. So object is equal to binary shifted to the right 8 bytes. But we want to AND it, much like we did before with this particular value, so that we are sure that we don't include the flag if the flag was set. And this will be a good test case for that. Last but not least, the sub-object. There's no shifting to do because it's already in the right. We basically just take the object and we AND it with this. And that should basically give us the value that we put in. So if we were to ask this thing for the information that we had before, we could basically call unpack the data, flag, obj, sub-obj, get those 3 values out, print them, and make sure they match the original arguments. And this can basically confirm to us, standard printing here, this should be able to confirm to us that we did it properly. We end up here with 0. That's wrong. So this was fun. I get to expose... I love how every time I try to make a video, I just make the most confusing test cases. I hope you guys get to learn from this because these are never straightforward, and I never plan them properly, but whatever. I should at least teach you what the hell happened so you learn something from it. I've been staring at this for like 5 minutes because like this is impossible for this not to be true. And sure enough, it is. This again was how you check to see if this bit has been set. The problem is the result of this is not just 1 or 0. It's a number that overflows this binary, this 8-bit number result, and therefore it comes out 0 when it shouldn't be. In other words, one way to fix this would be if this expression is non-zero, return 1, otherwise return 0. This would return the proper result. I think a smarter thing to do in this case would just be, instead of trying to be crafty and checking to see if the bit is set, doing the same thing I do below by shifting it to the right and then ANDing it instead, which would be a lot simpler. In other words, binary, undo the left shift 31 that I do above, so shift it to the right 32 bits, and then check to see if it's just set to the first position. This at least allows me to be A, consistent, and B, not have to worry about overflowing the number. So, after some really stupid debugging and feeling really dumb, the result works. The number that we packed in, which was 1, 1,000,001, and 120, indeed is extracted properly in our unpack function. This might seem extremely unnecessary to you just to store 3 numbers when you could just have 3 variables, and I will agree that in absolutely most cases that is true. Doing this for the sake of doing it will not make you look cool. It will create unreadable code, and it can be very dumb to do this in modern cases. But if you have cases where you absolutely need or cannot fit any more information, for example, encoding this kind of data in a 32-bit color in a picture or a texture map on the GPU, or encoding this kind of information in a network-based game where you know your throughput or bandwidth is absolutely limited, like a multiplayer tank game, where you need to have all this information and every single bit matters. It is very valuable to know how to do this. It's very powerful, and C is definitely the language to practice this kind of stuff in. So this video ran long. This was supposed to be short, but I hope I did you guys a service by actually walking you through some of this stuff. It took me a few years since I learned C before I started feeling comfortable actually working at this level, working with the bits and bytes. But once I got confident with it and felt better, it's never natural to me. You know, I never really work at this level that much, but it's very useful to know how to do this. So I hope you guys enjoyed this video, and you know, as time goes by, hopefully I'll be able to put out more of these little Swiss Army knife technique-based things for C. So thanks for watching.